All right, now, despite the idea that energy is quantized, physicists continued to picture emitted energy as traveling specifically in waves. All right, and so we still weren't able to explain all the aspects of electromagnetic radiation, which led us to this next part, which is the photoelectron effect. Now, you notice that I keep saying physicists, and this is a chemistry course. This is one of those topics that, as chemists, we do need to understand, but that crosses that barrier into physics. Quantum mechanics is very much physics, but we still have to know some of it for chemistry. Actually, we have to know quite a bit of it, but physical chemists are like that kind of crazy combination between physicists and chemists. Anyway, okay, back to the story at hand. So the next thing that was looked at that just did not fall completely under a wave-like definition is what we call the photoelectron effect. All right. So the photoelectron effect, we get a flow of current a flow of current when monochromatic light of sufficient frequency shines on a metal plate. Okay, so that was the next thing that just this wave-like definition didn't completely explain. That continued to look like we were seeing some particle behavior as well. All right, and so our photoelectron effect, that light shining on a certain metal plate caused a flow of electrons, i.e. we get this current that starts happening when we get this monochromatic light. All right, so a couple of things though. This light had a minimum frequency. Not any color would work. So notice I said it was monochromatic light, and so it had to be the right frequency. And bright light caused more electron flow than weak light. Electron flow started immediately as long as you are at the right frequency. Okay, so what does this look like? Well, we started to try to understand what was going on here. So we had this minimum frequency, and we knew that no matter what, as soon as that light was shined, whether it was bright light or weak light, we would get that electron flow. Okay, and so there were a couple of confusions here. Confusion one was what we call this threshold frequency, that minimum frequency that we would need in order to get that, to work. So the minimum frequency, so this was our threshold frequency. Okay, and then again, we saw this, electron flow immediately with strong or weak light. So it started immediately. And so the other thing is, one thing that we didn't quite understand was this absence of a time lag. Okay, and so Einstein made another proposition that light itself is particulate. Okay, so Einstein proposed that light itself is particulate. And what we get is that it's quantized into small bundles of electromagnetic radiation called photons. Okay, so light itself is particulate. Okay, light itself is particulate. And so it's quantized into small bundles. Later called photons. Okay. All right, so here I have a diagram of what this can look like. Is I've got light shining in, and as soon as the light hits the metal plate, the electron flow starts, and it hits a detector, and we can figure out the electron flow. So our electrons can be ejected from some metals when they're exposed to light. Now, is light behaving like a particle, which can bounce electrons out of atoms? Light can behave as both a wave and a particle, and we get that quantization of energy the same either way. All right, so again, this goes back to this wave particle duality. Okay, so we get a wave particle duality there. Okay, so when we talk about that threshold frequency, again, not all colors work. It has to be the right frequency. Okay, we've got some stuff going on. So I've got the energy of my photon, that packet of light, is equal to Planck's constant times the frequency, which tells me that that's also the change in energy of the atom. And this makes sense because if my photon is this little packet of energy, well, when something comes in and hits my metal, it's hitting the atoms, all right, and electrons are bouncing out. And so my atom has to change energy in some way, shape, or form for that to happen. All right, so I get this threshold frequency. So I've got my energy of the photon, and then in order for the electron to bounce out, because the electron's held in there, right? So it's got some binding energy. And so the electron, in order for it to bounce out, the energy that is hitting it has to equal the binding energy of that emitted electron. So a photon of sufficient energy must be absorbed for an electron to be freed, okay? So a photon of sufficient energy must be absorbed for an electron to be freed. Okay? And so each atom changes its energy whenever it absorbs or emits one photon. Okay? And so this photon is one particle of light whose energy is fixed by its frequency. Okay? So our photon is this particle of light, and the energy has to do with the frequency because this is equal to the energy of my photon. I'll make myself a little bit more room. And this is all equal to the change in energy of the atom. Okay? All right, so I have light with a wavelength of 200 nanometers. We've got some sodium atoms, and those sodium atoms have an ionization energy of 496 kilojoules per mole. And I want to know, how fast are those electrons that are being emitted? Okay, so our ionization energy, okay, that's taking a look at part of what is holding the electrons on there. In order to ionize, you have to overcome a certain amount of energy in order to get those electrons out. So what does this all look like? Okay. So we've got the energy of our photon was equal to that. Okay. Now, what this is equal to the energy to knock the electron out of orbit plus the kinetic energy of the photon. Okay. Or we've also got still equal to that. Look at this as the ionization energy. And the kinetic energy of the electron. Okay? Because remember, with our first law of thermodynamics, we learned that the energy of the universe is conserved. And so the energy taken in by one thing needs to be equal to the energy emitted out by another thing. And so if I am taking in a photon, and that is a minimum amount of energy to knock the electron out, then my energy of my photon has to do with the energy of the electron too, because we're taking it in and then we're bouncing the electron out. The atom's absorbing the photon and then the electron's popping out. Okay? All right, so, and then that IE, if you don't recall from prep chem, that's ionization energy. Okay, so I have ionization energy in kilojoules per mole of electrons. Okay, I need to figure out a single electron and I need to put that into joules. So we're going to look at our ionization energy and do some conversions first. All right, so that's my ionization energy. And 1 mole of electrons is 6.022 times 10 to the 23rd individual electrons. And then I have 1,000 joules in every 1 kilojoule. And this is going to give me 8.24 times 10 to the negative 19th joules per every single electron. Okay? All right, now the energy of my photon. Okay, the energy of my photon is going to be the hc over lambda, because I know Planck's constant, I know the speed of light, and I was given a wavelength. So we're going to take our 6.626 times 10 to the negative 34th joules seconds times 3.00 times 10 to the 8th meters per second, and 200 times 10 to the negative 9th meters. Okay, this is going to give me 9.93 times 10 to the negative 19th joules. Okay, so here's something really important. I have 10 to the negative 19th and 10 to the negative 19th. Okay, this is really important that the order of magnitude here be the same, because I have this relationship up here. The energy of my photon is equal to the ionization energy plus the kinetic energy. Now, if these were not the same order of magnitude, the additive property here would be useless. If these were vastly different orders of magnitude, one would far outweigh the other, and we wouldn't need to consider both. But we do have to consider both, and they're both the same order of magnitude. So it's very important that you stop and check yourself here and make sure that these are at the same order of magnitude. Okay, and so what we get is we get this kinetic energy of the electron, we'll rearrange, is equal to the energy of my photon minus the ionization energy. Okay? Now, why do I care about the kinetic energy? Well, kinetic energy is 1/2 mv squared, v being velocity, and we're trying to figure out the speed. Okay, I'm going to give myself some more space to write. Okay, so my kinetic energy of my electron, I'm going to take the photon minus the ionization energy. So my photon was 9.93 times 10 to the negative 19th joules minus 8.24 times 10 to the negative 19th joules for that one single electron. And I get 1.69 times 10 to the negative 19th joules. That looks good so far. Okay, and then kinetic energy, again, is that 1/2 mv squared. Okay, so we're going to get 1.69 times 10 to the negative 19th. Now I'm going to go ahead and turn this joules into my kilogram, meter squared, second squared. 1/2. Now we're talking about an electron, so the mass of an electron, 9.11 times 10 to the negative 31st kilograms times velocity squared. Okay, this is mass of an electron. Okay, and then it's just a matter of doing math to solve for V, and you should get 6.1 times 10 to the 5th meters per second. And there's the speed of our electron. All right, so now we've looked at two situations where electromagnetic radiation being simply wave-like doesn't work, that we're seeing this particle-like behavior. We have one more piece of the story before we've completed understanding this section. All right, we're not done with this whole chapter yet. There's more to it than that. But one more piece of the story to understand this wave-particle duality and the observations that led to us understanding that there is a particle-like nature to electromagnetic radiation. So that's coming up next.